Welcome back to Meteorology, our survey of the wonders of the weather. In the last lecture, we learned why we have a chance at having life on Earth, the atmospheric greenhouse effect. That involved absorption and emission of radiation, one of the three ways that heat can be moved around on Earth and through the universe. Before we review, I have a few questions for you. What causes the seasons? Here's a hint. Most Harvard graduates get this one wrong. Why does a metal spoon feel cooler than a drinking glass when both have the same temperature? When we touch it with our hand, why do we tend to dramatically underestimate the temperature of the sea? And why does beach sand get so hot on a sunny summer day? The answer is surprisingly complex. Why is that same sand so cold just before sunrise? So here's the story so far. Temperature differences make pressure differences cause winds. How and why do temperature differences arise? An even more elementary question, how does heat energy move around? We're considering this in a step-by-step process. The primary energy for the Earth atmosphere-ocean system is the sun. That energy reaches us through space by radiation. Being hot, the sun's radiation is concentrated primarily in the shorter wavelengths we've termed shortwave radiation, ultraviolet, visible, and the near-infrared. As this radiation passes through our atmosphere, it can be reflected back to space, scattered around, or absorbed. Some radiation, in the ultraviolet, is absorbed by oxygen and ozone, but for the most part, air is a poor absorber of shortwave radiation. So a substantial fraction of the sun's energy survives to reach the ground, where it is much more readily absorbed. The ground is nearly a perfect absorber. The ground is a black body. As a consequence, although the sun is out there in space, to a very large degree, the atmosphere is heated from below, like a pot of water on your stove. This is why the warmest temperatures in the lower atmosphere are found near the ground and decrease swiftly with height. This was the portion of the atmosphere we called the troposphere. The temperature only stopped decreasing with height because of absorption of ultraviolet in the stratosphere. Without oxygen and ozone to intercept much of that shorter wavelength ultraviolet radiation, the Earth would be a very different place. In this course, we will see that the variation of temperature with height in the troposphere plays a very important role in the weather. That variation of temperature with height is in part a consequence of differences in how air and Earth absorb radiation, and also in part consequence of how the atmosphere moves heat around. Also crucially important is the fact that radiation is not equally distributed across the Earth's surface. Instead, the tropics receive much more solar radiation than the poles. This creates a temperature difference between equator and pole. Since temperature differences make pressure differences and pressure differences drive winds, the equator to pole temperature difference is the primary driver of the atmospheric circulation. And it's all a consequence of the fact that the Earth is spherically shaped. So I'm going to do an example with a flashlight. And I'm going to turn the flashlight on, and I'm going to point the flashlight towards the table. I'm producing a certain amount of light. And this light is basically striking the table over a relatively small area. And this represents the direct radiation that is received by the tropics. But if I tilt the beam of the flashlight, I'm not producing any less light than I did before, but now it's spread over a larger area. So any single piece of this area that is being illuminated is actually receiving less energy. And as a result, is absorbing less energy here at the surface, and this represents the poles. So since the Earth is spherical, the sun's rays are less concentrated at the poles. They're making a more acute angle to the ground, and that's the primary reason why the poles are colder. This would be true even if the Earth didn't have an atmosphere. But atmospheric effects compound this problem in direct and indirect ways. While absorption of sunlight by the air is pretty limited, the amount of solar energy that reaches the ground can be reduced by reflection and scattering. So the potential for this loss depends on the sunlight's path through the atmosphere. In the tropics, the sun passes nearly overhead during the day. This decreases the distance sunlight has to travel through the atmosphere. But at the poles, the light makes a much more acute angle with the ground as a result of the fact that the sun travels lower in the sky. So the path taken through the air is longer, and that increases the chances for losses along the way, reflections and scattering and things like that, making the amount that actually reaches the ground even less than expected. A further complication arises from the fact that the Earth's axis is tilted. We call this obliquity. Our present tilt of the Earth's axis is 23.5 degrees from the vertical, but this varies between 22 and 24 degrees over a period of about 41,000 years. Owing to this tilt, both hemispheres spend part of the year inclined towards the sun and part inclined away, and this causes the seasons. So we're looking at northern hemisphere summer. At the North Pole, the sun's rays are still coming in at an acute angle at the pole, but more directly than they would have if the Earth were not tilted. So the poles are relatively warmer in the summertime. Tilting away from the sun creates winter. When one hemisphere tilts away, the other is tilting towards, so obviously seasons will be opposite on either side of the equator. Our winter is southern hemisphere summer. But that's not the only complication. The Earth's orbit is also eccentric. Eccentric means that the Earth's orbit is not perfectly circular. There are periods of the year when we're relatively closer or farther away than our mean distance of 93.5 million miles. This is sometimes confused as the reason for the seasons. But keep this in mind. What time of year are we actually closest to the sun? Actually, it's in January, during northern hemisphere winter. So eccentricity is a very small complication. Here is the recipe: no tilt, no seasons. So let's retrench. Temperature differences make pressure differences drive winds. The intent of winds is to reduce the temperature differences that gave rise to the pressure differences in the first place. One major source of the temperature difference is unequal heating of the Earth's surface owing to the Earth's round shape. There is a seasonal variation as well. The temperature difference is relatively smaller in the summer than the winter owing to obliquity, but at no time is the pole ever warmer than the equator. The average winter surface temperature at the North Pole is minus 30 degrees C, or minus 22 degrees Fahrenheit. An average year-round temperature in the tropics is about 25 C, or 77 F. This makes an equator to pole temperature difference of almost 100 degrees Fahrenheit during wintertime. If the purpose of winds is to reduce temperature differences, if the purpose of winds is to eliminate imbalances, smooth out inequities, and yet we still have a 100-degree Fahrenheit temperature discrepancy between the equator and pole during the winter season, shall we conclude from this that nature is not very good at what she does? Should we believe that perhaps nature doesn't abhor extremes as much as I might insist? And I say the answer to that is no. Before we convict nature of slackness or failure, we should consider what the Earth would be like if nature didn't at least try to address heating imbalances. A very ready example is our immediate neighbor, the Moon. The Moon is also an unequally heated sphere. But the Moon has no atmosphere. There are no winds to move heat energy around. Our wintertime temperature difference between equator and pole may seem very large at 100 degrees Fahrenheit, but the Moon's equator to pole temperature difference is closer to 500 degrees Fahrenheit. So nature may not be as successful as we might like, but it has already accomplished a great deal with the atmosphere, its winds, clouds, storms, and all of her other tools. Yet, it's still worth considering why nature hasn't done better for us. This leads us to study the obstacles and frustrations that nature faces. One of these is the fact that the Earth rotates, but we're getting a little ahead of ourselves. Before that, we need to understand how and why local temperature differences can lead to local winds and what those winds are able to accomplish. In this lecture, we have two more goals. First, to appreciate that other ways of moving heat energy around besides radiation also exist and why they're not equally important, and to determine how quickly an object heats up or cools down when exposed to that radiation, since that helps make local temperature differences. So the sun's energy reaches us through the empty vastness of space via radiation. This is a very efficient means of transporting energy that does not require mass as a medium. There are two other mechanisms of heat transfer we need to consider: conduction and convection. Both require a medium. In our case, we're concerned with air and water. But first, let's consider a question. What is heat? We often think of heat as a property. So we say something that is hot has a lot of heat. But properly speaking, heat is a flow of energy between objects. The property we're thinking of is actually internal energy, and temperature helps us measure that property. We want to move that property around, and that is the subject of what we call heat transfer, a term which ironically still treats heat as a property. Central to the discussion of heat transfer is a concept called heat capacity, the ability to hold heat, another legacy of archaic thinking. I will break free of this past by using a different term for heat capacity in the discussion that follows. But I will likely wind up treating heat as a property like everyone else, which isn't correct, but it certainly seems very sensible to us. So let's talk about conduction. Conduction is heat transfer by direct atomic contact, atoms and molecules touching each other. Conduction operates in one direction, from warm to cold. Recall we discussed that temperature is a measure of microscopic kinetic energy of atoms and molecules, vibration, translation. For us, we can just think about the vibration part of that. When warmer or more vibrant molecules and atoms come in contact with cooler, less vibrant ones, some microscopic kinetic energy is transferred from the warmer object to the cooler one. So heat is transferred from warm to cold. I find it helpful to picture a billiard table and balls moving around. This is macroscopic kinetic energy. But what happens on the billiard table when faster and slower balls collide? Does the faster moving ball speed up as a result of the collision? No, it slows down instead, and part of its macroscopic kinetic energy is transferred to the ball that's moving with the smaller speed. So there has been a transfer of kinetic energy from the ball with the excess to the ball with the deficit. Conduction, in a sense, is atomic billiards. Conduction involves transferring not macroscopic kinetic energy, but microscopic kinetic energy, as measured by temperature, from the object with more to the object with less. Thus, conduction moves heat from warm to cold. The next important point is that objects differ in their ability to conduct heat. I have a metal spoon and a drinking glass. Both of these have been sitting here for some time, and they have the same temperature. But if I touch them, I feel a temperature difference. Which feels cooler? The spoon feels cooler than the glass. But they're at the same temperature, so why do they feel different? The reason is that metal is an excellent conductor of heat. The spoon feels cool to our touch because it's taking heat away from our skin quickly. I am warmer than the spoon, and the spoon is conducting heat away from me. Materials that are dense and with highly ordered atomic structures, like metal, are generally very good conductors. They're very good at playing this game of atomic billiards or atomic dominoes. This is why we use metal pots and pans in cooking, to quickly heat the food in the pan by the metal. Iron is good, aluminum is better, and copper and silver are the best heat conductors of all. In contrast, glass is a pretty poor conductor. It takes a lot longer to heat food up in a glass pan. The glass is not conducting the heat to the food as quickly. But food stored in glass will keep its high temperature longer. since the glass is slower to conduct that extra heat away. So our old saying is cook with metal and serve with glass. And slow cookers use glass-lined pans for the same reason. In that case, it does not matter if things actually heat up quickly or not. So now let's consider an example using water and air. You're perfectly comfortable in 70-degree Fahrenheit air wearing light clothing. But if you were immersed in water at that same temperature, you would feel very cold. In fact, prolonged exposure to that water would kill you. Why? First of all, we need to consider that water at this temperature is 26 times better at conducting heat than air is. And since the temperature of the water is lower than your body temperature, you're losing heat to the surroundings. Your heat loss to 70 Fahrenheit air is pretty slow and you can deal with it because air is not a very good conductor. But the heat loss to 70 Fahrenheit water is much more of a problem because it's a lot faster. Even though we should keep in mind that water is still 650 times worse at conducting heat than copper. The point of this is that air is a terrible conductor of heat. Now that's not all bad. Air is actually a very good insulator. It's good at stanching heat transfer. It's good at slowing heat loss. In fact, air is the secret to some of our very best insulators. Here's a piece of fiberglass insulation. You probably have this in your attic. What makes fiberglass insulation a great insulator is the fact that there are many air pockets between the fibers of the insulation. If you want to prove that, all you have to do is compress the fiberglass down and make it as thin as possible. Squeeze out the air and close up those air spaces, and you'll find that it does not insulate as well as it did before. Igloo snow houses are another example of a good insulator. Snow is a terrific insulator because the irregular structure of snowflakes helps create air spaces that trap air. Woolen sweaters also trap air in the fibers of the wool. And cork pads that we use on our kitchen tables, the secret is lots of air pockets. The consequence of air's poor conductivity of heat is this: air does not carry heat away from a heated surface very quickly. Example, beach sand on a sunny afternoon. The sand can get very hot, but the air, even a few millimeters above the sandy surface, can be much cooler. The air is not taking away the sand's excess heat very efficiently because air is a lousy conductor. Then picture what happens if the tide happens to wash up. How quickly does the sand cool off then? Even if the water were the same temperature and density of air, the sand would cool much faster, due in part to water's much larger conductivity of heat. So, heat conduction through air is too slow, too inefficient to be a useful way for nature to move heat around. In fact, if you waited for conduction alone to heat your broth for dinner, you might starve first. And air is a much worse conductor than water is. But in thinking about heat transfer, conductivity isn't the only property we need to be concerned with. The next concept is called thermal inertia. Inertia is resistance to change. By analogy, what I will call thermal inertia is resistance to temperature change. Objects with large thermal inertia can absorb a lot of energy without their temperatures rising very much. You've probably observed that objects that tend to warm up quickly also cool off very quickly as well, and vice versa. That's thermal inertia at work, resistance to temperature change, up or down. This concept is usually called heat capacity, the ability to contain heat as if it were a property. Let's use sand as an example. Sand has a very low thermal inertia, so back on our sunny, warm afternoon, the sand can get very hot. It got hot during the day because the sand could not resist the temperature rise as it absorbed solar energy from the sun. Overnight, that same stretch of sandy beach will get very cool. It gets cold at night because it cannot resist the temperature drop as it loses energy via radiation. Now, we need to consider a point of potential confusion. Heat conductivity and thermal inertia are not the same thing. This is a pretty subtle point. The afternoon sand feels hot because it is a good conductor, and it's giving you its heat very quickly. The sand is hot because its thermal inertia is low. In fact, if the sand did not have a low thermal inertia, it would not have gotten so hot in the first place. In fact, it might have even felt cold to you instead of hot if its thermal inertia were very high. So now let's contrast sand and sea. Owing to its low thermal inertia, the temperature of sand can have a very large diurnal cycle. At the same time, the sea surface temperature doesn't change very much during the day. One reason for that is the sea is translucent to sunlight, and it has an internal circulation. When the sunlight reaches the sand, you're just heating up the top millimeter of sand or so. Dig a couple of inches beneath the surface of the sand, and you'll see that the soil there is much cooler. But when sunlight lands on the sea surface, you're warming up water that is absorbing the solar radiation, but then that water is replaced by other water, by an internal circulation. And so actually you're mixing that heat over a greater depth. As a result, the ocean is a huge reservoir of heat energy, as well as water. And the thermal inertia of air is somewhere in between sand and sea. So here's a question. On that sunny beach, if air were a better conductor of heat, would the sand get as hot as it does? Let's analyze this situation. It's a warm, sunny day. The sand is a far better absorber of solar radiation than the air above it. So the sand is absorbing energy that the air is not. Is this why the sand gets hot? That's not enough. Further, the sand's thermal inertia is low, so this energy absorption causes its temperature to get high. Now we've finished our answer. Sand's a pretty good conductor, and it's willing to share its heat with the cooler air molecules that come bumping on by. But air is a poor conductor, so it does not share its bounty of heat energy acquired from the sand with other air molecules above very quickly. Let's take a look at a vertical profile of temperature very near the ground. Here is Stickman, and I'm using Stickman for a sense of scale. The horizontal axis here is temperature, from cold to warm. The vertical axis is height, from the surface to a little above Stickman's head. Stickman can use a few pounds, and I can lend him a few. But what this graph shows is that temperature can get very hot near the ground over that sandy surface, but it decreases very quickly with height. The air at Stickman's head can be quite a bit cooler than the air at his feet or at his knees. I'm showing 120 Fahrenheit at the ground and only 90 Fahrenheit at head high. If air were a better conductor, it would take heat away from the surface more quickly, so the sandy surface would not have been able to get as hot, and the air at Stickman's head would likely be warmer as well. So now I'm showing you what the temperature profile might look like if air were a better conductor. Notice that the temperature near the ground is now cooler than it was before, but the temperature at the height of Stickman's head is actually warmer, because the heat has been shared more equally through the lowest layer of the atmosphere. So air is not a good conductor. So heat transfer in any direction needs some help. And we call that help convection, heat transport by mass fluid motion. Convection comes from the Latin word to carry, to convey. Basically, I'm talking about the wind. One way that the wind can cause vertical mixing and vertical heat transport occurs as the wind courses over irregular surfaces, mountains, hills, trees, houses, buildings, things like that. This creates eddies that transport hot air up from the ground and transport cooler air down to the surface. The same can occur as air passes over land that has been irregularly heated, some places getting warmer than others, perhaps because you have concrete, you have grass, and places with different thermal inertias. So due to convection, a windy day can accomplish what conduction cannot. and that is to make the sandy surface cooler than it otherwise would have been. So now you're looking at a temperature profile with height for a windy day, and notice that again the temperature near the ground is lower than it would have been if the air were calm, and the temperature at Stickman's Head is higher as a result. At night, sand's low thermal inertia permits the sand to get cold, and this will chill the air near the ground. But warmth from above is not conducted downward very quickly. In this plot, we're seeing what we call a temperature inversion. When temperature increases with height, we call this an inversion because it's the opposite, it's the inverse of what we've come to expect, which is temperature decreasing with height above the ground. Technically, this is called a radiation inversion, as it's caused by radiative cooling of the sandy surface, exacerbated by the low thermal inertia of sand. But as we've also seen, it's also exacerbated by air's poor conductivity. If air were able to share its bounty of heat from a few feet above more efficiently, it would not get so cold at the sandy surface at night. But that's for a calm night. When the wind kicks up, again, there's more likely to be vertical mixing, this time leading to relatively warmer temperatures near the ground and cooler temperatures farther aloft. So on a windy night, it's likely to be not quite so cold at the sandy surface and likely to be a little colder at Stickman's Head. Okay, a few more questions. Under what conditions are we most likely to get really cold temperatures at the ground? I can think of 4 of them. First, when the air is relatively dry, there's less water vapor to trap outgoing long-wave radiation, which is part of the greenhouse effect. Other things being equal, less humid nights are cooler than more humid nights. Second, when the sky is clear, no clouds to absorb outgoing long-wave radiation and return some of that to the surface. So other things being equal, clear nights are cooler than cloudy nights. Third, when the surface has a low thermal inertia, sand and concrete will get colder at night than grass and water, other things being equal. And fourth, when the winds are calm, because this limits the vertical mixing of air and helps to maintain the surface cooling. So let's summarize what we've discussed in this lecture so far. We have a large temperature difference between equator and pole because the Earth is spherical. That temperature difference is exaggerated in the winter season because our half of the sphere is tilted away from the sun at that point in time. Axial tilt causes the seasons. The winter equator to pole temperature difference, 100 degrees Fahrenheit. Without the atmosphere and its circulation, though, that temperature difference would be a heck of a lot larger. There are 2 other ways of moving heat around. Both require a medium. Conduction, atomic billiards. Convection, carried by the wind. Conduction is slow, in air at least, because air is a lousy conductor. But that makes air a great insulator. We examined a concept called thermal inertia, resistance to temperature change. Objects that heat up slowly tend to cool off slowly as well. Liquid water has a huge thermal inertia, and as a consequence, our oceans are also huge reservoirs of heat energy and not just water. Many land surfaces, in contrast, I've been using sand as an example, has low thermal inertia. It heats up fast during the day, and it cools off fast at night. So let's look ahead. Temperature differences play a critical role in meteorology. One way to make temperature differences is to provide surfaces that differ in some critical aspects. Suppose they receive more or less solar radiation, owing to Earth curvature and tilt, such as the equator and the pole, winter and summer. They could also differ in how they absorb solar radiation, due to differences in reflectance. Consider a shiny surface versus a dark surface. One of the reasons why snow can persist so long is it reflects away so much of the solar energy due to its brightness that would want to melt it. These surfaces could also respond to the energy that they absorb differently, owing to differences in thermal inertia. They also can differ in how they conduct heat away when they're hot and receive heat when they're not. One way to mitigate temperature differences created by differences in latitude, differences in season, differences in surface characteristics is to transport heat by mass fluid motion, by convection, by the winds. We can create winds and mixing through mechanical and thermal processes and transfer heat far more efficiently than through atomic billiards. Temperature differences make pressure differences, and pressure differences drive winds. Here's a question for you. When the winds blow, is heat also forced to move from warm to cold? In the next lecture, we will see that the quintessential local circulation responding to temperature differences owing to radiation and conduction is the sea breeze.